In this video, I'm going to show you how you can use QuPath to segment nuclei and identify positive cells for a given staining with a watershed-based method. So first of all, I'm going to open an HTab image. So if I go back to the images directory, I'm going to open the Chi67. So it's a bright field image that has been scanned with a Hamamatsu scanner. You see it's NDPI. And so the good thing is that QuPath can recognize this kind of formats. So it's an HTab with tab for Chi67. It's for lung, tissue. I can import it. I can open it by double clicking on it. First thing, if I go to image, now I have all the metadata. So I know what's the pixel width and height, and then I can know, of course, the actual width and height, and every single annotation or measurement we're going to do will have the real measurements. So first thing I'm going to do is to do the stain deconvolution. So I'm going to zoom in, define a small area where we have tab, hematoxylin, and background, like in here. And I can do Control L, estimate stain vectors. Yes. And I can do it auto. So you see now we have blue and brown for tab. Okay. And I can visualize different components here. So hematoxylin and tab. All right. So I'm going to remove this annotation. And I'm going to define a not too large region where I have both. So let me check. Like in here, we have a region without tab. Here we have tab. And I'm going to run the positive cell detection tool. So if I do Control L, I can type in the cell. So you can do the cell detection, where you're going to only segment cells with a watershed-based approach, or positive. So it's the same thing, but you can also identify positive cells. So here we have all the different parameters. First of all, which channel we're using, hematoxylin or optical density cell. We'll go back to it. The requested pixel size. So here we want to identify nuclei that are small, so we're going to need the full resolution. So that's, we saw that it was 0.45, so that's what we want. We could increase this value and it would speed up the segmentation, but we would lose some information. So it's probably better to get a very high resolution. Then we have different parameters for the segmentation. So first in the pipeline, there's a background subtraction. So we have a background radius here and the max background intensity. So basically, we don't want to be perturbed at what's in the background. And here the idea is to apply a minimum filtering, meaning that at each location, we look in a small neighborhood and we take the minimum intensity in this neighborhood. So somehow it shrinks the objects. And so we're then less dependent on the background. The second parameter is a median filter. If we do a median, so the radius for median filtering, that might be helpful when you have some texture maybe, but it's a bit hard to interpret because in the pipeline we already have a background subtraction and then a watershed. So I won't use this and keep it as 0. Then we have the watershed. So the watershed consisting of first filtering the image with a Gaussian filter with this kernel size, and then thresholding. So those two parameters. Basically, it's a threshold. It's fairly straightforward. The higher it is, the less nuclei we'll have. The lower it is, the more cells we have. For the sigma, if we take a low value, we're going to over-segment nuclei. If we take a large value, we're going to under-segment nuclei. Then we have this parameter split by shape. So I think it's the binary watershed that you can find in Fiji, for example. So if you have a shape that doesn't make sense, basically if it's a non-convex shape, it's going to try to split it a little bit. It's not really non-convex, but most of the time that's the idea. You can exclude depth of the membrane staining. I'm going to just keep it that way. And then you have the parameters. So we segment the nuclei, but then we artificially expand the nuclei to get an area for the cell, which might be interesting for the intensity threshold. So I'm gonna, in our case, the staining is in the nucleus, so we actually wouldn't need to do expansion. So if you uncheck that, you would only have the cell expanded. Here we have both nucleus and cell. We could remove the expansion because we're only looking at the nuclei, but that will allow us to look at what we have. So I'm going to keep that way. And then you can smooth boundaries and make measurements. So smooth boundaries, it's going to visually be a little bit better. So it's fine. And make measurements, it's interesting if you want to do some measurement, if you want to extract measurements associated with your cells, like cell area, perimeter, or the value in the different channels. Finally, you can threshold to find the positive cells. So either you do a single threshold, that's what we're going to do, but we could look at several thresholds, a low, a medium, and a high. So then you have negative cells and you have 1 plus, 2 plus, and 3 plus. So you can compute a H-score. Here we're just going to take a single threshold. In that case, those two parameters are not used, only this one. And all the cells that are segmented and then have a value superior to that for this core compartment. So in that case, it's the average staining of DAB that is superior to 0.2. They're going to be positive. We can change that. So that's where expanding the cells can help. So you can look at the average of the max. You can also look at the average of the max in the cytoplasm, or the average or the max in the cell. So as I said here, we're only interested in DAB, which is staining the nucleus. So we can keep nucleus DAB. So I'm going to first process it this way. So run it. So it's quite well implemented, so it's pretty fast. And so it's running in the entire annotation. And these are the results. So you see the negative cells are in blue, the positive cells are in red. Okay. So as we are interested in the nuclei, something we can do is changing in the view to only visualize nuclei. It's easier to get an idea about what's segmented. And something you can directly see is that these cells that are positive for DAB are not segmented. It's because we're looking at the hematoxylins. If we go back here, I just look at hematoxylin for this cell, for example, I have nothing. And it's just because the DAB is blocking the hematoxylin, so when we do the deconvolution to estimate DAB and hematoxylin, we don't have anything in the hematoxylin, but we have something in the DAB. So one way to work around this is actually to use a different measurement, the optical density sum, which is a combination of both. So if we go back here we don't have anything. Here we have a strong staining for DAB. If we do optical density sum, we have a strong signal. Now if we look at the ones that are that only have hematoxylin, like in here, so in that we have nothing, of course, but optical density sum we still have quite strong value. So instead of hematoxylin, we're going to use the optical density sum. I can run it again, and then we can see if we have something here. It should be the case because it's quite strong in the optical density sum. And here we are. So now I have the nucleus here. It's definitely better. So you can look at the optical density sum, which makes sense because that's what we're taking into account in the segmentation. You can go back to the original. You can switch between the two. So I'm going to keep this because most of the people are more used to have this visualization. But don't forget that's what is taken into account. Okay. So as I said, main parameters, sigma and threshold is most important. So if I get a small value for sigma, I'm gonna over segment the nuclei. So I'm gonna have very small or divided nuclei. And clearly you see here, we have several parts and even lots of missing parts just because maybe we filtered them out. I forgot to talk about those two parameters. Here we have minimum and maximum areas. All the nuclei have an area inferior to 10 micrometers are filtered out. And the ones that have an area superior to 400 are filtered out as well. So here we over segment. If I take a large value for sigma, I'm going to under segment. So like even let's say 5. We're going to have very large regions. Now you see we are merging together nuclei. So not all the time. Now here it's fine, but clearly, like in here, it doesn't make sense here either. And if we go in the region where we have small, it's interesting because it found things with the nuclei inside, but that's clearly not a good parameter. And we are merging together. Nuclei that should be separated. So I'm gonna go back to something like maybe 1, 2. So this looks better. So we might have a segment. We also have this nuclei. So you can, so again, you can use with transparency, but you can also switch on and off with this. And this is not. This doesn't correspond to nuclei. So I'm gonna increase the value of my threshold. See if I can get rid of this. And that looks better. That looks better. Maybe I over segment still, so I'm gonna go to 1.1.5. Now with watershed, you will never get something perfect. It's always a trade-off between different parameters. So it's easier to move only one parameter at a time because here we have quite some parameters to understand what we're doing. And sometimes it's gonna work, but sometimes it's not gonna work. And that's really a trade-off between those kind of things. So here I guess threshold I can increase it because this is nothing. This is nothing, I think. So let's try this. Now, it would be a good idea to try several regions even to see, what are the parameters that give you the best results, even though it won't be possible to get something perfect, that's for sure. Okay, so let's say we're happy. So the last thing we can do is change the threshold. So here, if I increase it, I'm gonna have less DAP positive. So some DAP positive cells that are for now they're gonna become DAP negative. And so here it's clearly too high because we definitely should be positive. This as well. I think the previous parameters was fine. So I'm just going to run it again. And so again, it's not perfect. I'm sure we could improve the results as well. But I'm not going to spend too much time here. Something that is important is that when you're working with your images, you also know better what they correspond to, especially for regions that are not non-specific. Like in here, we see that we have some DAB in the background that can perturb the segmentation, and that's the kind of things you need to look at. And probably when you work on your images, you're probably the best placed person to do that. So I'm gonna use these parameters, and first I'm gonna remove that. So if I go there and delete the annotation, then there's a hierarchy of objects in QuPath. So you have the annotation, and then you have the objects inside, so under the annotation. So that's why, so I remove the annotation, and now QuPath is asking me if I want to keep the descendant objects, meaning this detection that are below the hierarchy of this annotation. I don't want to keep them because I'm going to segment the whole tissue. So here I'm going to say no. I removed everything. All right, and now I'm gonna first define the tissue. So you can use the wand when you are at this resolution. That's pretty nice tool. You need to find the right resolution. So here here it's not great. It's okay. I'm gonna just remove them later on. So let's say it's fine. I want to go back here. If I use the Alt key, I can do probably something better like this. Alright. Let's say here, definitely don't need that. Let's say it's fine like this. Alright. Let's keep adding. So there would be probably more efficient ways to do it, faster ways, but that works. So here, maybe I can go fast like this. Alright, and maybe just removing this. Alright, so that was not perfect, but let's say I'm okay with that. Why did I do that way? Because now you can have the area where I'm doing the segmentation. So, maybe it would be better to remove this. So obviously you could do a pixel, you can train a pixel classifier to recognize tissue versus the background. That would work pretty efficiently. Here is just to show you that when you have several annotations like this, you can select them all, right click, go to annotation, and then you can do operation on multiple and like merging one. And the good thing is that now I have only one annotation. I have total area for this annotation, for example, and I can run the watershed on the whole area. So I'm going to run it. When you start running, so you see you have it's working on individual tiles like this. It's tiling your entire tissue. It's been very well implemented, so it's running in parallel. So it's using the different cores on the CPU to do one tile on each core. And so even though it's a very large tissue, it's gonna be pretty fast, So I'm just gonna speed up the video now, so you don't have to wait the entire processing time. Alright, so it took about 10 minutes to run the whole slide. So it takes some time, but considering the amount of data, it's not that bad. I'm gonna close the positive cell detection now. And first of all, so we also computed the measurement, and that's what takes time at the end, I guess. So what does that mean? If I zoom in on the cell, so now we can visualize again the cell boundaries. Just to, so it makes sense if I double click on one, so I select the cell, and I have, so the coordinates of the centroid, the area, perimeter, circularity, max caliper, min caliper, eccentricity of the nucleus, so these are morphological features, and then I have the average hematoxylin, sum, standard deviation, maximum, minimum, and range of hematoxylin. Same thing for DAB, and then same thing for the cell, same thing for the cytoplasm. So we have quite some measurements that could be used for other things, or you can also extract them and do your stats afterwards. You can see that I have quite some, so I should have increased my threshold probably because it's very sensitive in the DAB. Anyway, let's say that you're happy with everything you did. Now, as we have one annotation, we can look at the measurements associated to the annotation. So if I do show annotation measurements, I'm going to have one measurement. So that's pretty heavy. I guess we have lots and lots and lots of nuclei. The nice thing here is that you have the area and the perimeter of your tissue, and then you can know how total number of detections. In that case, it's let's see, 1.5 million cells, the number of positive and negative, so the percentage of positive. And as we have the area, you also have the number of positive per millimeter squared. Might be interesting as well. So here, it's really a nice way to summarize all the information on your tissue, about your tissue. But if you want to have all the measurements for each individual cell, you can go to show detection measurements. In that case, every single line corresponds to a cell, and so then you know if it's negative or positive for DAB. And then you have all the measurements, so what we saw already, coordinates of the centroid, area, perimeter, circularity, all of this about the nucleus, then the measurements about DAB and hematoxylin in the nucleus, toxinin, and then same thing for the cells and cytoplasm. You also have, if you want to know what it corresponds to, you can double click here. So here we don't see because we're very low resolution. So if I go at this resolution, for example, if I double click even on another one, I can see where it is in the image. So let's look for a positive, for example, and so on. All right.